Great. Yeah, great. So my name is Joe Perguna,
Yeah,
and we're presenting on knowledge graph prediction of adverse drug reactions with drug substructures and drug protein binding affinities. So a little bit of background: why predict adverse drug responses or reactions? 64% of hospital admissions and 10% of patients have ADRs during a hospital stays. Policy to observe and document also during a drug development process. It's difficult to determine long-term ADRs and short-term trials.
yeah, and we use this data structure called a knowledge graph, and it turns out a knowledge graph is really useful because it helps you represent connections between data that otherwise would be really difficult to account for. So, for example, nodes represent entities, and the edges are kind of information about those entities. So one example that we found here, which is not, it's not related to proteins and adverse drug effects, but it kind of shows what a knowledge graph is. For example, you want to represent the relationship between the actors, the movies they acted in, and also like what character they were. So you have three kinds of nodes: actors, characters, and movies, and then three kinds of edges that kind of store the relationship between them. Yeah. So in a similar way, we construct this knowledge graph in which we have drug nodes. We have nodes that represent drugs, ADRs, so adverse drug reactions, the disease for which a drug has been prescribed for, and also this is all this has been researched before, but like on top of that, we are adding information about proteins that a drug binds to, because that actually can offer meaningfully insight into the toxicity of the drug, and also molecular structural information of the drug.
Great. So some preliminary work, as Alexander mentioned, has been done using knowledge graphs to predict ADRs. So a previous paper that we built our procedure based on used protein targets, indications, ADRs, and nodes in a knowledge graph. So our question was, can we prove this accuracy by including more additional information? So our 5 areas were: first, to gather new drug-related information. Second was to augment the existing knowledge graph to include drug substructure information. Third was to augment the graph to include drug protein binding affinities as weights on edges. The fourth was to reduce the graph complexity, because we anticipated that these additions would create a much more dense and highly connected graph by clustering similar proteins based on binding pockets. And our fifth aim is to evaluate these predictions with reference to the original team paper.
Yeah, so firstly, we had to gather all the data to predict this knowledge graph, and it was a lot of data. We used we basically to parse databases that contain data about drugs, their side effects.
Can you move just slightly?
Yeah. The disease they're prescribed for, and also some binding databases that can give us the interaction between drugs and proteins, as well as like that actual value of the binding activity. For that, we chose the CIDR database for the drug adverse side effect and indications of disease here, and PDB bind for the binding information. We kind of needed a way to construct this database such that it's going to be easy to query the edges, and it's also going to be easy to work with in Python. So we kind of put a lot of time into building this Postgres database. That would kind of, I think would actually be helpful to others in the field too, because we end up actually gathering a lot of entries. That would be the results section.
So for our second and third aims, we're talking about the augmentations of the existing knowledge graph. So the first augmentation regarding the substructure inclusion. So we added these new indicator nodes that are used to predict these unknown drug responses based on an OpenBabel FP2 fingerprint. So you basically have about 1,000 substructures there that you can use to create like a binary vector of whether the substructure is included in a protein or not. So you can use this as like a fingerprint for different molecules. And this modification greatly increased the size of the graph, which is something we anticipated. Second modification involved a binding affinity modification, which is a more substantial modification to the actual graph and to the algorithm that analyzes the graph. So we replaced these binary edge weights with edge weights that were based on a negative log of the KD of a protein drug binding. Because in the previous Bean algorithm, they calculated adjacencies. They calculated enriched nodes when doing binary classification based on how many shared nodes two nodes had in edges to. So we wanted to ensure that small KDs representing tight affinity would increase the would be a sign of a strong affinity similar. So we got our KDs, as Alexander mentioned, from PDB bind, but there are many missing KDs, unfortunately. So this required a severe modification of the processing enrichment step in the algorithm.
The fourth aim was to, as we also mentioned a bit before, try to reduce the size of the graph, but not by removing what we just added, which was drug substructures, but rather by trying to collapse the protein targets into protein pocket families somehow, because the intuition here was that if two drugs have similar toxicity, they might be binding to similar pockets. So even if two proteins are very different, if their pockets are similar, then we kind of want to reduce the active noise that is included from the rest of the protein. So what we did is we specifically used PDB bind because it contains the PDB files for the pockets, protein pockets themselves. So, and that's actually quite rare. I didn't find any other database, and also these ones were not very good. They had a lot of formatting errors. And the idea was based on the structures of this protein pocket, we would cluster the proteins in like families based on their similarity. So the new nodes in the graph would be rather families of proteins rather than proteins themselves.
Yeah, so we experimented with two different techniques, APOC, which uses the actual atomic positions of atoms in the binding pocket, as well as the chemical similarity of the aligned pockets to calculate the similarity score between 0 and 1. We also experimented using BLOSUM, which is something we're familiar with in this class, the chemical similarity of aligned sequences. The goal was to use hierarchical clustering on these generated distance measurements after the fact to determine these binding pocket motifs or clusters.
Yeah, we're gonna get them in the same order. So the database was, we created this huge database that has like 1 million edges. The proteins are not we're going to the limiting factor here because of the PDB bind database. We were able to leverage a lot of the cyber database. So we have like 10,000 drugs and thousands of substructures and side effects and disease. It's also the repo in which we implemented this provides I would say like an easy way to visualize the data because it was needed when we work with like huge amounts of data. We believe that if others are like other people interested in the field that want to work with such data, I think this would be good because previous papers used they also like put together a knowledge graph, but there were a lot less edges, and we thought that being able to try to run your predictive algorithm on multiple different data sets is useful. So this could actually be partitioned into a lot of knowledge graphs.
The results of the actual augmentation. So the first addition of the substructure augmentation showed that, so the left here is the initial Bean. This is a K-fold across validation, and the bottom shows the proportion predicted in the original model and the count. So the left shows 10% of the graph, and the right shows our result on the same 10% of the graph. So we showed pretty much an equivalent performance, including the substructure, which is actually pretty surprising. On the right, we see one selection of a drug that the initial Bean paper pursued later for validation and literature. We showed the green is our modification area under the curve calculation, blue is there. So we have a slight increase in the performance of our model with this protein. We used all the proteins they validated in literature and selected for as candidates. as good ADR drug predictions and showed that our model outperformed their model, but was not statistically significant. So in terms of the augmentation of the binding affinities, we were unsuccessful in implementing this. We developed a modification to the graph that would accept the data, but because of some limitations that we're using, we did not have sufficient KD data to perform that augmentation. So the next steps would be probably to abandon the binary classification. There's been a lot of work because the current graph model required a separate binary classifier to be trained for every single ADR node within the graph. It was really costly, very computationally heavy. So there have been some work in the field of knowledge graph completion, abandoning these individual binary classifications.
Yeah, and there were also some problems with with the reduction of the graph size. And again, it was kind of it was a data limitation, simply because, as I said, the bind database that we used, because it was the only one that we could extract pockets from, had a lot of formatting errors, and so the frameworks that we use in order to kind of establish a similarity measure and compute it between pockets could not parse those paths correctly in many cases. And the second problem would be that in the other, this was in the Blossom procedure, and the other procedure in which we were kind of only looking at the atom coordinates instead of the actual sequence. The tool required the volume of the product pocket, which PTM didn't really have. So this was a project with a lot of data intensive. But we believe that maybe it might be valuable to explore another version we didn't have time for, and that is to identify the protein pockets ourselves by setting a threshold in what's the distance, you want to look at all the atoms in the protein that are a certain distance from the ligand in the complex, and consider that to be a pocket.
All right, we're already at 12 minutes.
Yeah.
So basically, it doesn't seem to be improving.
Yeah,
is that
the surprising? He added a lot of information. There have been some previous papers that have shown.
Can you tell which of the information is most useful to then tune it down?
Yeah.
Basically, maybe some of the existing information was not very useful, and some of the new information is not very useful.
Yeah.
If you prune it to the most informative features.
Yeah, I think that there would be a way to do that. So the step, when you train the binary classifier, you calculate enrichment based on certain nodes. So you get a list of enriched nodes. So I think looking for overlap in that enriched set to determine which nodes are actually being used as predictors. Yeah, that's a great idea.
And another idea would be, because we actually included all of the substructures that we would get in the fingerprint, but a lot of them might be noisy and just not useful. So, and there's research out there that kind of is trying to like mine patterns and graphs. So maybe another step is to use that in order to filter out only the most important structures, and then.
Can you switch to the next pages? Great.